gravity is capable of producing waves. Now, we've never seen these things. So the challenge is to see them. And just like other forms of wave, you get frequency. So, I can talk like this, or I can talk like this. You can change the frequency of sound. And for light, the analog of frequency is color. Blue is at one end of the frequency, red's at the other. So you can change the frequency of waves. So gravity waves come in different frequencies, caused by different events. So the analog of red would be the waves of gravity that were caused around the time of the Big Bang. Now, can we see those? That's a question. Or you can consider supermassive black holes. There are these things called black holes that are predicted by the physics. You could imagine looking at supermassive black holes as they interact with galactic nuclei. Can you detect those kinds of waves? The frequencies are going to be different. Or you could look at things like binary stars in our galaxies. And so there's a whole range of frequencies in which these waves can occur. Question is, can we find them? And that's what I'm going to close on. Well, first of all, it's more math, right? Because that's what Einstein actually gave us, a piece of mathematics. And it's those of us who like to play with mathematics, beat the math to death to get it to tell us a story. And then we go talk to our friends who are very clever at measuring things, because typically those of us who are really good at math are terrible at measuring. It's almost an exclusion principle. And so you have to talk to people who are really good at measuring things. And your friends who are really good at measuring things go out and build these very sophisticated devices. Although the LHC, which measures the Higgs, was not invented for measuring gravity, it's one of the most complicated devices that has ever been constructed. So you talk to people who can build complicated devices. And like I said, normally the people who understand the math are not the people who can build devices. And there's a third group that's sort of in between the two. In our community, we call them phenomenologists. So the people who understand the math, they understand devices, they kind of act as the glue to make sure that the whole edifice works to discover new science. So this is what the math of these waves look like. It's this last thing. Let me point out, there's a factor of 2 here, whereas when I looked at electromagnetic waves, there was a factor of 1. And when I looked at sound waves, there was no term like this at all. This is again telling us we can track the spin of these waves by looking at the trigonometric dependence on a certain variable. So, in March of this year, there was an announcement. The announcement was that an experiment called BICEP-2 had seen evidence of gravity waves in the early universe. So how do we translate that to ordinary people speak? Because we're all ordinary people here. So the idea is, if I had a cup of latte, and I put a spoon in it, and I stir the cup up, if I look at the suds and foam on the top of the latte, I can see the pattern there. And so the idea here was that in the early universe, remember in our radiation picture, we always saw these modes that were looking like circles? If they were there in the early universe, they would have stirred the early universe. And therefore, any picture taken of the early universe would show the evidence of this stirring. And that's what the BICEP-2 experiment was claiming, that they could see the evidence of the gravitational waves stirring the early universe by looking at the cosmic microwave background. That's what was up. Now, unfortunately, we now think that that was wrong. And I wish David Spergel was here, because this is really in David's realm. David was here last year, and in fact, he and I talked a bit about various things related to this. But there's lots of evidence that they blew it. Because we humans aren't perfect. We cannot do everything perfectly all the time. It's just not in our human capacity to do. So in science, we try to do the best we can. And as we tell you scientific stories, they're the best possible things we can tell you at the time. So BICEP-2 didn't seem to find this effect, but there's another experiment called Polar Bear where they may be seeing this effect. There's a recent piece of research out that maybe they're seeing the stirring in the cosmic microwave background caused by these primordial gravity waves. So these are some pictures of the actual, this is the BICEP-2 experiment. This picture is an illustration of the Polar Bear experiment. What other ways could you see these waves? Well, I have a little movie here. In this movie, what we imagine are 2 stars, but not 2 ordinary stars, but 2 massive neutron stars that are orbiting about each other. Now, neutron stars are very interesting because they have these beam-like structures that come out top. If they're massive enough, they will generate waves of gravity. And if you, unfortunately, the lights are too high, but you can kind of see there's some kind of something here that's rolling, and it's coming to like a familiar blue marble and its companion, namely us, passing the moon. And when this wave gets to the ground, if it's really there, it's going to do something. Now, if it happened to hit at two places in the United States, one in the old Hanford Nuclear Reservation in Washington, or near Louisiana, New Orleans, it'll come down and find an L-shaped building. This L-shaped building is a scientific experiment called LIGO, the Laser Interferometry Gravitational Wave Observatory. All of you who are taxpayers in this room, you spent probably by now about $500 million on this. So you might want to know where some of your money went. This is where you were spending it. Actual pictures of LIGO look like this. On the left of this, we have the site in Johnson Parish in Louisiana, north and west of New Orleans. On the right, we have the one in the state of Washington at the old Hanford Nuclear Reservation. As you can see, it's a big L-shaped building. And if you watch the end of my movie, what you would have noticed is that the building was not at rest. It was actually flexing. And the reason that it was flexing is because these waves from the neutron star, if the mathematics is right, tells us that space is flexing. But if something is in space, then that thing has to flex. And so the idea with this experiment is that you can measure the flexing in this L-shaped building, 1.7 kilometer long arms. You can try to measure how the arms are stretching when one of these waves comes down and strikes it. Now, the changes that you're trying to measure are remarkable. They're like 1,000 times smaller than the nucleus of a helium atom. That's pretty small. And so LIGO has been in operation. It's just recently had an upgrade that will allow it to continue to run. And we're looking for the effect of these waves. So the waves will be changing the lengths of these arms. We use lasers, by the way, to measure the lengths. That's why it's Laser Interferometry Gravitational Wave Observatory. And we're looking to see, do these two arms get a little bit shorter and smaller in a way that's consistent with this mathematics? That's a hard experiment, clearly.